Good evening, everybody. Am I audible? Am I audible? Then please give me thumbs up in the comment box. Yes, let me see. Yes. Am I audible? Please give me a response in the comment box. Am I audible? Am I audible? Yes. Okay, fine then. So good evening once again. So we are Goscore Learning. We are the fastest growing edtech in GCC. Our aim is to provide education for all. So as part of that, we have started a live series on YouTube through our official YouTube channel. So today this is second class of grade 12 physics, and in this class we will discuss the fourth chapter, moving charges and magnetism, and its second part. So the first part of this chapter has been in our YouTube channel. Those who missed the first part, do watch the first part also, then you can follow the second part also as well. Okay, so before I starting the session, let me say something regarding, so what is the speciality of yesterday? So yesterday we celebrate as National Teachers Day, right? So we celebrate National Teachers Day on September 5th, as it is the birthday of our previous President of India, the second President of India, Dr. Sarvepillai Radhakrishnan, right? So he is a well-known educator, he is a good teacher. That is why we celebrate his birthday as National Teachers Day. So for all of you dear students, you were celebrated some functions, some function will be there in your school, and you honored your teachers. So as a teacher, and I am standing in front of you, and I am very glad to interact with you. And while I am teaching you physics, I will remembering my physics teacher, though, Mr. Dhanaraj, who teach me physics in my grade 11th, and he is a good teacher, and I inspired of him, and I choose the field physics. And when I choose the field physics, I never think that I will be a teacher, but later when I completed my post graduation and all, I choose my passion, and I understand that my passion and profession will be teaching. So on this equation, on the day after the Teachers Day, National Teachers Day, I remember all of my teachers who have inspired me a lot. Not only Dhanaraj sir, I remember all the teachers who inspired me from my nursery or kindergarten or in my first standard as well. Okay, so for you all, there will be some teachers who inspired you as well, right? So be glad to your teacher, or be thankful to your teacher. There are some teachers who will become as role model for you, right? So teaching profession is such a noble profession, and I am very glad to interact with you standing in front of you to teach physics. Okay, so welcome to Goscore live session. So as I said, this is our second part of the chapter 4 of grade 12 physics, moving charges and magnetism. Okay, so in the previous class we were discussed about Biot-Savart law as well as magnetic field on the axis of the circular current law. Okay, so these are the main two topics that we have discussed in the last class. Okay, did you remember Biot-Savart law? So we can just recollect that. Okay, so Biot-Savart law gives measurement of magnetic field due to a current element. So what is current element? Okay, let me explain. Okay, so consider a current carrying conductor SY. Okay, so current carrying conductor SY carries a current of I ampere in the upward direction. Okay, so our aim is to give an expression for magnetic field due to the small current element dl. Current element. So what is current element? What is current element? It is a small length, and which is a part of the current carrying conductor, which carries a current. It carries a current, the same current as I. So it's a small length. Okay, so called it's a vector quantity. Okay, so Biot-Savart law gives the amount of magnitude due to this current element dl at a point P. Okay, at a point P, we wish to find the magnetic field, so that we can mark the distance to the point P from the middle of the current element dl, and that is marked as vector R, position vector R. Okay, dl is a vector and R is a vector, and the angle between them is theta. Okay, then Biot-Savart law gives, these are names of two scientists, that's why the name Biot-Savart law. Okay, so Biot-Savart law gives the amount of magnetic field due to this current element is dB. dB means B is the letter used to denote magnetic field, right? B is the letter used to denote magnetic field. Then dB means small magnetic field, and which is equal to mu 0 by 4 pi I dl sin theta by r square. So this is the equation given by Biot-Savart law. So what is mu 0? Sir, it is the permeability of free space, sir. It is the permeability of free space, and it's a constant mu 0 by 4 pi, and whose value is, what is the value of mu 0 by 4 pi? Its value is 10 to the power minus 7, and unit is Tesla meter per ampere. Okay, I hope you are remembering all those things. Okay, so ideal sin theta by r square, and in vector form we can write it as dB is equal to mu 0 by 4 pi I into dl, vector dl cross vector r all divided by r cube. So this is the Biot-Savart law in vector form. So it is a vector, magnetic field is a vector. Okay, so you can see in the equation a sine angle, sin theta dependence in this equation. So when sin theta is 0, when theta equal to 0, sin theta equal to 0, right? When theta equal to 0, sin theta equal to 0. Sin 0 is 0. So what's the implication of that one? Okay, so consider this as the axis of the current element. Okay, if I considering the point P on the axis, what happen if I considering the point P on the axis? What happen? This R will lies on the axis, right? R will lies on the axis on the same direction of current element dl. Then what will be the angle between dl and r? If R lies on the same axis as that of dl, they will be in the same direction, and theta will be 0. Theta will be 0. So sin 0, 0. So a point which is on the axis of the current element, the magnetic field at that point will be 0. So that is a serious point and it to be considered. Okay, so these points we have discussed in the last class. Okay, so one more thing. So magnetic field on the axis of a circular current loop. Okay, so here I have a circular current loop, and its plane, the plane of this circular current loop is made perpendicular to the plane of the board, what I am considering. Okay, so we wish to find the magnetic field at a point P, which is on the axis of the circular current loop. What is axis of a circular loop or a circle? For a circular loop, axis means a lane passing through the center of the circle, and that lane will be perpendicular to the plane of the loop. That is what is called axis. Okay, so on the axis of the circular current loop P, which is at a distance x from the center, and the radius of the circular loop is r, and the circular loop carries a current I, then magnetic field due to the circular current loop on the axis is given by mu 0 ni r square all divided by 2 into r square plus x square all raised to 3 by 2. So this is the equation that we have derived in the last class, right? So what is n here? N is a number. Which number? Number of turns of the coil. If the coil consists of only one turn, n will be 1. If the coil consists of 2 turns, n will be 2. And I is the current, r is the radius of the circular current loop, and x is the distance in which we are considering magnetic field. Okay, so this is what we have discussed in the last class. One more point. At center what happened? At center, when we considering this point P on the center of the circular current loop, what happened? This distance x will be 0, right? So at center x will be 0. So what happen if x equal to 0? X equal to happen 0 means what happening is B will be equal to mu 0 ni r square all divided by 2 into r square plus 0 square all raised to 3 by 2, which means r square all raised to 3 by 2. 2 and 2 will be cancelled, and you will get it as r cube, right? r cube. Again we can, which implies B will be equal to mu 0 and some terms will be cancelled, right? Mu 0 r square and r cube will be cancelled, right? So the remaining term will be mu 0 ni by 2r will be the expression for magnetic field at the center. So please do remember this equation. This equation is very, very important so that we can solve some numericals. Okay, so this equation is very, very important so that we can solve some numericals. Okay, so please mark this equation as very, very important one. Not only this one, you should remember the equation for Biot Savart law as well as magnetic field on the axis of the circular current law. Okay, so please keep it in mind this equation mu 0 ni by 2r, which is the magnitude of magnetic field at the center. Okay, and magnetic field, we know that magnetic field is a vector quantity. For the first equation, the direction of vector dl cross r, the direction of vector dl cross r will give you the direction of magnetic field. And how can we find the direction of a vector product? Using right hand screw rule, right hand screw rule, and that we have learned in the 11th grade, right? So if you have any confusions regarding that, please do watch the previous video or previous part of this session, and in that session we have discussed about the right hand screw rule, right? Okay, is that okay? Then please give me thumbs up, we can continue. Okay, please give me thumbs up, let me see. Okay, yeah, okay, fine then. Okay, so we can move to a question. So it is a CBSE sample paper question which is given in the year 2023. Okay, so what is the question? Two concentric and coplanar circular loop P and Q have the radii in the ratio 2:3. Loop Q carries a current of 9 ampere in the anti-clockwise direction. For the magnetic field to be 0 at the common center, loop P must carry. 4 options are given. Okay, did you understand the question that is given? So remember, it is a important question and it's given in the sample paper for CBSE 2023. Okay, so if there is any confusion regarding that, please pause the video and read the question again. Okay, then so ratio of the radius of P and Q is 2:3. So P has small radius. So I have provided 2 circles here. I wish to mark. So this is P and this is Q. Okay, so the radius of P and Q is given in the ratio. Radius of P is to radius of Q is given in the ratio 2:3, right? That is what is given. Radius is in the ratio 2:3, and we can say that if the radius of P is 2r, then 3r will be the radius of Q, right? So that's the ratio given in the question paper, in the question itself, right? So why I call it as 2r and 3r instead of 2 and 3? Why? Because you will understand while solving the problem. Okay, so is that okay? Then what, anything else is given in the question paper? Yes, question, yes. Loop Q carries a current 9 ampere. So current through Q is given as 9 ampere, which is in the anti-clockwise direction, right? So anti-clockwise direction. So what, these are the data that is given in the question. So what is to be found? For magnetic field to be 0 at the common center, which means there is a common center because they are the concentric circle, right? So at the common center, loop P must carry. So we need to find the current in the P so that the magnetic field due to P and Q should be cancelled each other. Okay, we know that magnetic field is a vector quantity, so it will follow laws of vector addition. So if some quantity, if the magnetic field due to the Q is in this direction, we know that only at the point center the magnetic field is acting along the axis, right? So if the magnetic field of Q is in this direction, coming from the plane and from the center, then it should be cancelled if and only if the magnetic field due to P is directed inverse through the center. So the magnetic field should be equal and opposite, then only they will cancel each other because they are vectors, right? So what we can say, magnetic field due to Q should be equal to magnetic field due to P and should be opposite. then only they will cancel each other. Then only for the magnetic field to be 0 at the center. If and only if they are equal and opposite, right? So what is BQ? BQ means magnetic field at the center. So we have the equation for magnetic field at the center as B is equal to mu 0 Ni by 2R. So we can use this equation here. So BQ means mu 0 Niq divided by 2RQ would be equal to minus because they are in the opposite direction, then only they will cancel each other. So mu 0 Nip divided by 2RP, right? So this is the equation which implies okay, so again we can write is equal to mu 0. What is n here? N means number of turns. There is no number of turns mentioned in this question, so that we can take it as 1. So 1 mu 0 into 1 means mu 0 itself. IQ is given, yes, IQ is given as 9 ampere divided by 2 into RQ. What is RQ? RQ is 3R, right? So it is 3R is equal to mu 0 again we can see mu 0 with a negative sign. Mu 0 n again means number of turns, which is 1 here. So mu 0 into 1, mu 0 itself. IP, what is IP? IP is needed to be found, right? Yes. What is the current through the P? Loop P must carry what current? So we can IP we need to find. Okay, divided by 2 into what is RP? RP is 2R. Now you got, I call it as 2R and 3R. Okay, so is there anything cancelled from this equation? Yes. Mu 0 is common, cancelled. 2 is common, cancelled, and R is common and they cancel. So what are the remaining terms? Let me see. Yes, 9 divided by 3 is equal to negative of IP by 2. Negative of IP by 2, right? Negative of IP by 2. So from this equation what we can write? IP is equal to rearranging it, what will you get? Can you guess in the comment box? Let me see. Is anyone coming the answer? Let me see. Yes. Okay, fine. Okay, so IP is equal to negative of, we can simply take the negative sign, negative of 9 by 3 into 2. It is in the numerator, so it will be in the denominator it is in the denominator, so that on the other side it should be in the numerator, right? So it is equal to negative 18 by 3, which is equal to negative 6. What is unit? It is current, right? Negative 6 ampere. So what I have got is negative 6 ampere is the answer. This is the current through P. IP is negative 6 ampere. So what is negative 6 ampere? What is negative current? What is mean by negative current? Is there any idea regarding that? We have any idea regarding that? Negative current, because current is not a vector quantity, right? Current have direction and magnitude, but it is not a vector. Why it is not a vector? It doesn't follow laws of vector addition. Current doesn't follow laws of vector addition. That's why it is not a vector quantity. Okay. So fine then. So what is mean by negative 6 ampere means here current in the loop Q is 9 ampere in the anti-clockwise direction and is taken as positive, right? So the answer contains negative signs because the current should be in the clockwise direction. So clockwise is here, clockwise is here, and magnitude is 6 ampere. So option D is the correct answer. Okay, so this is actually 1 mark question, and how much is the time we have spent it for to solve it? Okay, so each 1 mark is an important mark in your exam, so be careful. We take lots of time because I explained it. Okay, so you can solve it easily, right? If you have the equation B is equal to B at the center, magnetic field at the center is equal to mu 0 Ni by 2R. If you have that equation, you can simply solve it. Okay, again one more question is there. Okay, what is the question? A straight wire carrying a current of 12 ampere is bent into a circular arc of radius 2 centimeter as shown in figure A. Okay, so we have two figures. The second figure will become in another question. Okay, let's see. What is the magnetic field at the center of the arc due to the straight segment? This makes sense. Due to the straight segment. The question is asked not regarding the entire segment. It It is only asked about the due to straight segment. Okay, so straight segment, to understand it clearly, I wish to draw the figure A like this. Okay, so this is the current carrying conductor, carries 12 ampere current. This is the center, and the question was asked regarding what is the magnitude of magnetic field. What is the magnitude of magnetic field due to this straight segment? Okay, at the center. Okay, is there anybody knowing the answer for this question? It's a simple question. No more equation is needed. Why it is no equation is needed? Okay, we can simply recall the first. This equation, it says that due to a current element, magnetic field on the axis of the current element will be 0, because sin 0, theta is 0, so there is a sin term comes in the equation, so magnitude will be 0. So due to the straight segment, this is the axis of the straight segment, right? So this point center is in the axis, so magnitude will be 0. No need for any equation, we can simply solve it, right? So the answer for the first question is it is 0. Very simple, right? Very simple, right? So what is the magnetic field at the center of the arc? So at the center of the arc for the figure A, it carries a current 12 ampere, right? So current is I is equal to 12 ampere, and radius is also given. Radius of the circular loop is given it as 2 centimeter. 2 centimeter means you should definitely convert it into SI unit. 2 centimeter means equal to 2 into 10 to the power minus 2 meter. For every quantity you should convert it into SI unit, and only you can solve the problem. Okay, so what is the equation? At the center, right? So we have this is a circular current loop, even though only half part of it is visible. Okay, this is a circular current loop, and we are finding the magnetic field at the center. So for the center of a circular current loop, we have the equation. I said it? No, it's a very important equation. So yes, what is the equation? Yes, B is equal to mu 0 Ni by 2R is the equation. So what is the value of mu 0? It's a constant, its value is mu 0 by 4 pi, you know. Mu 0 by 4 pi, you know, it has values 10 raised to minus 7 Tesla meter per ampere. So what is the value of mu 0? Just multiply it with 4 pi now. So value of mu 0 is 4 pi into 10 raised to minus 7. And what is the value of n? N means number of turns. So number of turn is 1. No, it's not 1, because only semicircular loop is here now. We can say n equal to 1 if complete loop is present. Only half of the loop is present now. So n is equal to anybody put in the comment box. What is n? What is the value of n? Yes, value of n is half, because only half of the circle is visible here now. So n is equal to half. So half into, what is I? I is given as 12 ampere, right? So 12 divided by 2R. 2R is given as 2 into 10 to the power minus 2. Okay, so simple question, mathematical solution is needed. Okay, so 2 into 2, 4 cancelled. Anything else can say? Yes. 1 by 2 into 12 means 6. Okay, so what remaining is, it will be, okay, remaining is 5 into 6 into 10 to the power minus 7 divided by 10 to the power minus 2, which is equal to 10 to the power minus 7 into 10 to the power minus 2 into the denominator means 10 to the power 2. Okay, divided by nothing in the numerator, right? So we can solve it. Right? Okay, so pi into 6. Pi means 3.14 into 6. What is 3.14 into 6? 4 into 6, 24, 168, 3. Okay, so 2 points are required. So 18.84, right? So 18.84 mango, 84 banana. What's the unit? What's the unit of magnetic field? Sir, unit of magnetic field is Tesla. Sir. Yes, it's Tesla. Or Weber meter is the unit of SI unit of Tesla. So it is Tesla. Not only that, we have didn't mark the power, right? So into 10 to the power minus 7 into 2, which means 10 to the power minus 5 Tesla. Okay, Okay, 10 to the power minus 5 Tesla. So it's better to write 1.884. That will be the convenient form. So 1 point, so point should be there. 1.884 into 1.884 into 10 to the power, 10 to the power, 10 to the power. Here we have skip the point into left, right. So the power should be reduced, minus 4. Power should be reduced, sorry. Power should be reduced. Power should be reduced, minus 4. This is the answer. Okay. Easy? Yes, easy peasy. Okay, then, so I think this question is very simple, so that we can, okay, one more question is there. Would your answer be different if the wire is bent into a semicircular arc of same radius but in the opposite way as shown in figure B? Okay, that's why figure B is shown here. Okay, so let comment for option C. Okay, for option C, what's the only difference? Here, we consider the loop means the current for the figure A is moving in this direction. We can say in the clockwise direction, right? Current is moving in the clockwise direction. So whatever this one is moving in the anti-clockwise direction. What remaining else? The magnitude of current, magnitude, we have the equation Ni by 2R, right? Mu 0 Ni by 2R. N is same, half, N is same for all. Okay, so I current is same current is following, no? So 12 ampere is the current. Radius is same. So magnitude of all the values given in the problem are same, but the only difference is the direction of current changes. Direction of current changes means there will be a change in the direction of magnetic field as well, right? Because the direction of current determines the direction of magnetic field. Okay, so the current reversed, so that the magnetic field should be reversed, so that we can say same magnitude due to the figure B at the center O, there will be magnetic field with the same magnitude as that of this one, 1.884 into 10 to the power minus 4 Tesla. The same magnitude will be there, and whose direction is opposite to this one. Okay, so we can say same direction with, opposite direction with same magnitude, right? Same magnitude with opposite direction, Why this opposite direction is happening here? Opposite direction. Why? Because direction of current reversed. All the remaining things are same. N is same, I is same, radius is same. So only direction of current changes, so that magnetic field reversed. Okay, so it's a easy problem. Okay, then we can move to right hand thumb rule. Why we use right hand thumb rule? We have learned this rule in your 10th grade. So I wish to recall those concepts that you have learned in the grade 10. Did you remember that? So what's the purpose of using right hand thumb rule? Why we use right hand thumb rule? If anybody remembering it, please put it in the comment box. Let me see. Okay, those who are remembering the way we use right hand thumb rule, it is Maxwell's right hand thumb rule. There was right hand rule by Fleming's. It is not Fleming's right hand rule. It is right hand thumb rule by Maxwell's, and call it as Maxwell's right hand thumb rule. So anybody remembering this? Anybody? 1 second. Okay, so right hand thumb rule gives the direction of magnetic field due to a straight current carrying conductor. So way we use right hand thumb rule is because to find the direction of magnetic field due to a straight current carrying conductor. Okay, let us recall the concept. Okay, so to find the direction of magnetic field due to a straight current carrying conductor. Okay, imagine this is my conductor. This pen is the conductor. Okay, so hold the conductor in your right hand in such a way that there will be current in the conductor, right? So suppose the current is flowing upward direction. This is the direction of current. Then hold the conductor in your right hand and the thumb stretch in the direction of current. My stretched thumb is in the direction of current. So everybody please hold your pen in your right hand in such a way that there is an upward current and your thumb shows in the direction of current. Okay, then the remaining fingers that encircles the conductor. So here I have the remaining fingers which is grasp the conductor or holding the conductor, which is encircling it, and whose direction is, this is the direction of encircling, right? So this is the direction of encircling. So this will be the direction of magnetic field. So we know that due to a current carrying conductor, there will be magnetic field around it. So it may be either in the direction or in the opposite direction. So by right hand rule, we can easily find the direction of magnetic field. So the fingers encircle the conductor will show the direction of magnetic field. So if a current in the upward direction, so we know that there is a magnetic field around it. We know that magnetic field will be around it, and the circular magnetic field will have the direction. We can find it using right hand thumb rule. So hold the conductor in your right hand and thumb stretching in the direction of current, then the remaining fingers that is encircling the conductor will show the direction of magnetic field. Okay, so if I hold this yellow conductor, my fingers are encircling the conductor in this direction, right? So this will be the direction of magnetic field. On this side. What about this side? It is coming from it and it is going into it on this side. It is coming from it, right? This is coming from it, and this is going into it on this side. Okay, what happened if direction of current reverses? If a downward current is here, what happened? So there will be circular magnetic field, and whose direction is given by right hand thumb rule. Again, hold the conductor. Thumb shows the direction of current in the downward direction. So this is the direction of encircling, right? So this is the direction of encircling. So on this side there will be an inward going magnetic field, and on this side there will be a outward coming magnetic field. Okay, so due to a straight current carrying conductor, there will be magnetic field around it in a circular form. Okay, so there will be a magnetic field in the circular form. Suppose this is the magnetic field. Okay, so I wish to find what is the direction of magnetic field at a single point. This is a circle. So at a single point which is on the circumference of the circle, the direction is given by tangent to that point. So at this point, at a point here, the magnetic field direction is tangent to that point. Oh, if this is a direction of magnetic field, the tangent to that point will give you the direction of magnetic field at a single point, at a particular point on the circumference. Okay, so the tangent will gives you the direction of magnetic field. I hope you are remembering the tangent concept that you have learned in grade 10 maths. Yes or no? If yes, then please give the thumbs up. I can easily understand it. Okay, so tangent means a line passing through the circumference of a circle which touches the circle only at single point and which will be perpendicular to the radius of the circle. That is tangent. Okay, those who forgot all those things, please recollect it. Okay, so we are using right hand thumb rule. To find the direction of magnetic field due to a straight current carrying conductor. Okay, then yes. Ampere's circuital law. So it's an important law in this chapter, Ampere's circuital law. Okay, so before learning about Ampere's circuital law, I wish to recall the concept of Gauss's law that you have learned in the chapter 1 of grade 12 physics. Gauss's law in the chapter 1, do you remember? Electric charges and field. In the last part there is a Gauss's law which gives a measurement of, or the measure of electric flux. What is the letter used to denote electric flux? It is phi, right? Electric flux. Gauss's law gives a measure of electric flux. Okay, so what is flux? Number of field lines passing normal through the surface, right? So number of field lines passing through the surface. Okay, and electric flux is given by the Gauss's law, and it is equal to Q by epsilon 0. So this is the equation for Gauss's law, right? Total flux through a surface is equal to the 1 by epsilon 0 times the net charge enclosed by the surface. This is what is Gauss's law. In other ways, we can write surface integral of electric field is equal to Q by epsilon. So this is Gauss's law that you have learned in chapter 1. Okay, so here is surface integral, and for the application of Gauss's law we have considered a Gaussian surface, right? So read it as surface integral of electric field through a closed surface is equal to Q by epsilon 0. Q by Q means the net charge enclosed by the surface, and this is the equation for Gauss's law, and we have three application of Gauss's law in the first chapter, which is application of Gauss's law in a straight uniformly charged straight conductor. Second one, application of Gauss's law in uniformly charged thin plane sheet, and third one, application of Gauss's law in a uniformly charged spherical shell. So that you have learned in the chapter 1, right? So here also we have, similarly we have here Ampere circuit law, which is related to magnetic field. Okay, so which is related to magnetic field, and here Gauss's law, which is related to electric field. Okay, electric field E. So Ampere circuit law says that the line integral of magnetic field B around any closed path, and is equal to mu 0 times the current passing through the path. Okay, so what is the equation then? Line integral means line integral of magnetic field. So line integral means with respect to length. So B dot dl, both the B and the dl means current element. Okay, are vectors, and line integral of B dot dl, which means integration of magnetic field with respect to length. Okay, line integral of magnetic field around any closed path. So it should be, integral should be closed. Okay, so this is what is closed integral B dot dl. Okay, so some students who are belongs to PCB stream maybe get confused using this equation, but for BCM students, those who have maths as subject will be comfortable, right? Okay, then closed integral B dot dl is equal to mu 0 times current I. Mu 0 times current I. So this is the equation for Ampere circuit law. Okay, so it's an important equation. Okay, so we can compare simply with the equation that you have learned for electric. Gauss's law, E dot ds. E dot ds is equal to Q by epsilon. Okay, so this is Gauss's law in electrostatics, and this is Ampere circuit law in magnetostatics. So instead of B, we can see E. Instead of line integral, we have surface integral. Instead of current I, current is the source of, steady current is the source of magnetic field, right? Or current is the source of magnetic field. Okay, so since we are dealing with magnetostatics, which is dealing with steady current, so here I is the source, and here charge is the source, and here the constant is mu 0, and here the constant is 1 by epsilon 0. So just compare and study. Okay, so how can we read it is as closed integral B dot dl is equal to mu 0 times current I enclosed by the surface. Okay, I have mentioned that we have three applications of Gauss's law in the first chapter. Similarly, we have application of Ampere circuit law in this chapter, and not three, we have two applications: magnetic field due to a straight current carrying conductor, or application of Ampere circuit law to infinitely long straight wire. Both are same. Okay, another one we have application of Ampere circuit law to a solenoid. Is also there, but there was a derivation regarding third application, which is application of Ampere circuit law to a toroid, and which is now omitted by the CBSE from the syllabus. Okay. Okay, so here we have first application, magnetic field due to a straight current carrying wire, or the question may be asked like that. Application, discuss the application of Ampere circuit law to infinitely long straight current carrying conductor. The same question can be also asked like this: magnetic field due to a straight current carrying conductor. Discuss the case of magnetic field due to a straight current carrying conductor. Okay, so that we have a straight current carrying conductor. There is a current I in the upward direction. Okay, there is a current I in the upward direction. So where there is a circle, I will explain it. Okay, so we have to find magnetic field due to this current carrying conductor, right? So consider a point P, which is at a distance r from the conductor. Okay, so this is the point P, which is at a distance r from the conductor. Okay, so we wish to find the magnetic field at the point P. For that, consider an ambient loop. Repeat once again, consider an ambient loop. In the case of Gauss's law, we have considered, for the application of Gauss's law, we have considered Gaussian surface, Here we have the counterpart in the magnetostatics. Here we are considering not the surface, we are considering a loop. So since we are dealing with the current, okay, so consider an ambient loop in the form of a circle with radius r. Okay, that's why the red circle is there, and the circle is plane of the circle is making perpendicular to the plane of the board. That's why I have drawn it like a ellipse. Okay, so imagine that the circle I have considered, the ambient loop I have considered is in the plane of the ambient loop is perpendicular to the plane of the board. So we can't draw 3D diagrams. That's why I have drawn it like a elliptical circle or elliptical shape. Okay, so it have the radius r. Okay, so where we start with? We start with the equation of ambient circuital law in the closed integral b dot dl is equal to mu 0 I. Okay, so we can start with that. So yes, ambient circuital law is closed integral b dot dl, both are vectors, equal to mu 0 I. I enclosed, I means I enclosed, current enclosed in the loop. Okay, so this is the equation. So to apply ambient circuital law, we have to consider the derivation as two parts. Okay, first of all, just consider the term on the LHS. Okay, we can expand it. Okay, so first consider the LHS, we can expand it. Okay, so we can start from closed integral b dot closed integral b dot. So closed integral b dot dl. So what is b dot dl? B dot dl means closed integral. B dot dl means b dl cos theta, b dl cos. Okay, so b dl, we want b and dl. So for this point P, what will be the direction of magnetic field? We didn't know the magnitude of magnetic field, but we know the direction due to a straight current carrying conductor. We have not Fleming's, Maxwell's right hand thumb rule to find the direction of magnetic field, right? So hold the conductor in your right hand in such a way that thumb shows in the direction of current, and the remaining fingers which is encircling the conductor gives the direction of magnetic field. So here this will be the direction. If I am holding the conductor like this will be the direction of magnetic field. So at the point P, you can see that there is an ingoing magnetic field, right? So at the point P, there will be an ingoing magnetic field. So this will be the direction of magnetic field in this conductor. This will be the direction of magnetic field. This is the direction of magnetic field. Okay, so at the point P, what will be the direction? So since it is a circle, we can consider the tangent, right? So that tangent will be going into the plane. So I can't draw a vector which is going into the plane on the board. So instead of that, I wish to draw it like this. So imagine that this is going into the plane. Okay, so we need dl also, current element. So consider a current element near to the point P. Consider a small current element dl near to point P, and whose length is dl, and what will be the direction? I wish to take the direction same as that of B. So what is the angle between B and dl? If the two vectors are in the same direction or with one over the other or the same direction, what will be the angle between that? Angle theta is equal to, what will be the angle between that? What is the angle? Theta is equal to 0 degree, right? If two vectors are in the same direction, angle between the vectors are 0 degree. If two vectors are in the opposite direction, angle can be taken as 190 degree, right? Okay, so here B is there, dl is there, and what is the value of cos theta? Theta equal to 0 here. So what is cos theta? If theta equal to 0, cos theta equal to, what is the value of cos theta? Cos 0, what is the value of cos 0? What is the value of cos 0? Sir, cos 0 is 1, sir. Yes, cos 0 1, and cos 90 is 0. Cos 0 is 1 and cos 90 is 0. So which will be equal to closed integral BL into 1, BDL into 1, which means closed integral BDL is enough. Then is equal to, so here magnetic field B is constant. Why? Because I is constant. So magnetic field will be constant, so it can be taken out of the integration part. So which is equal to closed integral DL. So what is integral DL? We know that integral DL is equal to L. Integral DL is So close integral dl means integration for the entire length of the ambient loop. Integral dl, you will get it as length of the ambient, total length of the ambient. So here we have considered ambient loop in the form of a circle. Okay, so in the form of a circle with radius r. So total length of the ambient loop means the circumference of the circle. Total length of the ambient loop means the circumference of the circle, right? So what is the circumference of a circle of radius r? Sir, it is 2 pi r. It is 2 pi r. Yes, it is 2 pi r. So the total circumference is 2 pi r. So I can simply write p into close integral dl means we get it as 2 pi r. Okay, and call it as equation number 1. Okay, so this is for the LHS, and now we can consider the RHS. Okay, so now we can consider the RHS, and or we can simply equating it, right? So equating 1 with the main equation, what will we get? B into 2 pi r is equal to mu 0 I. I is the current here, right? So what is B? What is B? What is B? Mu 0 I divided by 2 pi r. Mu 0 I divided by 2 pi r. So now we have got an equation which gives the magnitude of magnetic field. So this is the application of Ampere's circuit law to a straight current carrying conductor. This is the final equation. As simple as that. Just consider Ampere's circuit law and expand the LHS side, and while expanding you will get the equation B into 2 pi r, and equate that one with the RHS and rearrange to get the equation for magnetic field. This application of Ampere's circuit law to a straight current carrying conductor. That is difficult to find or difficult to by heart the or following the steps in this derivation, sir. So while you are studying any derivations in maths or in physics or in chemistry, so study in such a way that you are studying to teach somebody else. So try to teach somebody else. It may be your friend or your friend in your class, it may be your sister or brother or any siblings. Okay, so while you are studying, study in such a way that you are studying to teach somebody else. So if you are trying in that manner, definitely we can learn the derivations easily. You will never forget it. Okay, so if nobody is no friend is not available nearby your home, or no siblings are there, be your own teacher. Be your own teacher. Just take a notebook, or if you have a board in your home, just learn the derivations. Just learn the derivation and take a class. Students will not be there. You are the here student and you are the teacher, and be your own teacher and teach the derivation to your own. Then you will be feeling easy to learn all the derivations in physics. Okay, so you are trying in that way, you will feel easy to learn physics. Okay, not only physics, you can apply the same principle or same concept for maths, chemistry as well. Okay, so here this is application of Ampere's circuit law for a straight current carrying conductor. Here we can move to the next one. So what is this? These are two representations of what? So first one is a into mark, second one is a dot mark. Is that simple as that? No, it has more importance. Okay, so how can I represent a vector? How can I represent a vector? So vector can be represented as a straight line with an arrow mark. Straight line with an arrow mark. Straight line with an arrow mark. Okay, the direction of this arrow mark shows the direction of vector, right? So by representing like this, I can represent any vector with any direction which is lying on the plane. Any vector which is lying on the plane, I can use this kind of representation, right? A straight line with an arrow mark, and the length of the line segment gives the magnitude of the vector, right? So how can I represent a vector which is perpendicular to the plane? How can I represent a vector which is perpendicular to the plane, which is either coming from the plane or going into the plane? Either coming from the plane or going to the plane. So this is the way in which we can represent a vector coming from it or going to it. So this is an into mark, right? So this one into mark. So this shows a vector going into the plane. Okay, so this is a dot mark and a vector coming from the plane. Okay, so you will feel easy that This is an into mark, right? So vector going into the plane. Into mark, a vector going into the plane. So this is how you can remember. Into mark means a vector going into the plane, or dot mark means a vector coming from the plane. Okay, if you remember the first one, this feel easy to remember the second one. So it's a trick. Into mark means a vector going into the plane. Okay, is that easy? Is that easy? Then not only for vector, we can use this for current as well. How to use for current coming from it or going to it, you can understand it easily. Okay, so yes, solenoid. So what is solenoid? So what is solenoid? Solenoid means a long insulated conducting wire which is wounded in the form of helix. A long insulated conducting wire which is wounded in the form of helix. Is wounded in the form of helix. So this is form of a solenoid. Take a long insulated conducting wire and wound it in the form of helix, and you will get a solenoid. Okay, so this is a representation of a solenoid, and the representation can be done like this. So this is the representation of a solenoid in a circuit. Okay, so this is a symbol for solenoid. Okay, so the importance of solenoid in magnetostatics is that when a current is passing, current is passing through the solenoid, it acts as a bar magnet. A current carrying solenoid can act as a bar magnet, and which will produce magnetic field along its axis. Only along its axis. What is the axis of a solenoid? So if this is a solenoid, a line like this along the length, this is the axis of the solenoid. Okay, so a current carrying solenoid act as a bar magnet, and whose magnetic field lines of force are along the axis, which means the magnetic field lines will be like this. Okay, so this is the magnetic field lines, and so this is the magnetic field. And one more thing, only the magnetic field is present within the solenoid, and just outside means an area nearby here, just outside the solenoid, the amount of magnetic field will be 0. Just outside the solenoid, the magnetic field will be 0, and there will be magnetic field inside the solenoid along its axis, and just outside the solenoid, the magnetic field will be 0. Is that okay? Then we can move further. Okay, so solenoid is a long copper wire or long current carrying conductor or long conductor which is wounded in the form of a helix. That is what is solenoid, and a current carrying solenoid can act as a bar magnet, and the magnetic field will be along the axis, and just outside the solenoid, magnetic field will be 0. Okay, then we can move further. Okay, then second application of Ampere's circuit law, magnetic field due to a solenoid, or application of Ampere's circuit law into a solenoid. Sir, you said solenoid, but we can't see a solenoid here. It's actually a solenoid which is places on the board, and it carries a current I, and current is coming this dot right, and this is into mark. A current is coming from it and going to it, so this is the solenoid, right? So I didn't represent it here. Instead of that, I have used representation of direction. So a current coming from it, going to it, coming from it, going to it, coming from it, going into it. So you can see a solenoid here. So you know that a current carrying solenoid produce here, the solenoid carrying a current I, and it will produce a current carrying solenoid will produce a magnetic field is coming from it and going to it, and magnetic field will be along the axis like this, and whose magnitude is given as B. Okay, so now we are going to define or derive the expression for this B. So what is that's the aim of this derivation. Now we are going to derive the expression for this B, magnetic field produced by a current carrying solenoid. Okay, so for that consider an Amperian loop. For the application of Ampere's circuit law, we need a loop, right? We need an Amperian loop in the form of, here we consider in the form of rectangle. Okay, in the form of rectangle, and I call it as A, B, C, So this is the rectangle. Okay. So consider an ambient loop in the form of a rectangle ABCD. Okay. So for the application of ambient circuit law, we have to start with ambient circuit law. What is ambient circuit law? This is given as closed integral B dot dl. Both are vectors. Vectors should be the equal to mu 0 I enclosed. I enclosed means total current through the loop. Okay, total current through the loop. Okay, so what we need to first, what we have to do in the first, so consider the LHS. Okay, we can expand it. That's what we have to do. Okay, so consider LHS. So what is LHS? LHS is equal to closed integral B dot dl. Both are vectors. Okay, B dot dl is equal to. Okay, so here closed integral B dot dl means this is our loop. So we have to integrate along the length of the loop. Along the length means from A to B to C to D to A. From A to B, then B to C, then C to D, then B to A. So that I can write like that. How can I write it like that? So is that okay for you? If I write it like integral from A to B, B dot dl, it's not over then, plus integral B to A, B dot dl, plus what will be next? Come on, put it in the comment box. Come on, yes. Yes, magnetic field due to a current carrying conductor at a point is equal to K, where I is the current, and yes, there is a definition given by Kuwait. I don't know. Okay, let us see. So what's next? Integral. Oh, sorry. Mark it as closed integral from B to C. B to C, right? A to B, then B to C. B to C. B dot dl again. Plus again. Then what will be next? From C to D. A to B, B to C, then C to D. C to D. B dot dl. B dot dl. Right? Is that over? Not over. D to A is also the right. Also add that. So I will write in the beneath integral D to A B dot right dot. Okay, so from A to B, then B to C, then C to D, and then D to A. Okay, after writing this, please follow me. Then left the first term there, we can consider the second term. We remain left the first term because we will understand it later. Okay, so just consider the second term. What is second term here? Okay, so second term means integral from B to C, B dot dl, B dot. So integral from B to C, B dot dl. Okay, so what is B to C? What is B dot dl? B dot dl means B dl cos theta. B dl cos theta. Theta means the angle between B and dl. Theta is the angle between B and dl, sir. Theta is the angle between B and dl. So this is the direction of B. Right, this is the direction of B. And what is B to C? B to C means this length, right? So what is the angle between that? Angle between is 90 degrees, sir. Angle is 90 degrees, sir. Yes, angle is 90 degree. So here theta is 90 degree. Theta is 90 degree. What is cos theta then? Cos theta means cos 90. What is the value of cos 90? Cos 90 means 0, sir. Cos 90 is 0. So B dl cos theta, you will get it as equal to integral B to C B dl into 0, B dl into 0, which is again is equal to 0, right? So the second term in the equation cancel. This get as 0. Then we can consider the third one. Okay, so let's go for the third one. Okay, again integral. Third one is from C to D. C to D, sir. Yes, B dot dl is equal to, expand it from C to D, B dl cos theta, Okay, what's the angle between B and dl here? Here this is the dl, right? C to D, this is the dl length, this is the length, and direction of B is in this side. So angle will be 180 degree. So what is cos 190? Okay, don't go for cos 180 because CD is just outside the solenoid, right? CD is lying just outside the solenoid. So what is the value of magnetic field just outside the current carrying solenoid? What is the value? Anybody, please, could you please comment in the comment box? What is the value? What is the value? What is the value? Its value is B0 here. B0 because magnitude of magnetic field just outside the current carrying solenoid is 0. So it is 0. So here B will be 0. So that the final, what will be the total one? B will be 0, then the total output will be 0. Okay. So second term is also solved. Then go for the third one. So what is the third one? Integral A to D, or sorry, D to A, right? D to A B dot DL, both are vectors, is equal to same as D to A B dl cos theta, sir. B dl cos theta. Yes, no need to put the vector symbol because B dl cos theta is a scalar product, so no more vector symbol is not required. Okay, so cos theta, B dl cos theta. What is theta here? So A D to A, right? D to A means this is the direction of D to A and B in this direction. So the angle is this is the direction of, this is the direction of L and this is the direction of magnetic field. So angle is 90 degree. Then 90 degree means cos theta, cos 90 is 0. So again it is equal to 0, sir. Again it is equal to 0. Okay. So the second, the third as well as the second, the third as well as the fourth term is 0. Okay. How simple is this? Okay. Let's see. Only the remaining term is the first one, right? First one. Okay. Let's integrate the first one. Let's take the first one. Okay. Integral. Okay. Sorry. Let me check the ink. Yes. Yellow one. Okay. So integral, close integral, no, close integral is not required because we are integrating from A to B, right? So A to B, B dot DL. B dot DL means vector symbol required is equal to integral A to B, B dl cos theta, B dl cos theta. So what is the theta here? So here from A to B, right? So this is from A to B and B is in the same direction. So theta equal to 0. Theta equal to 0. So cos theta equal to cos 0. Cos 0 is 1, sir. Cos 0 is 1, sir. Yes, cos 0 is 1. So you will get it as equal to, not required now, is equal to integral A to B BDL, integral A to B BDL. Okay, I will write it once again. Okay, so A to B BDL. A to B BDL means here B is a constant and can be taken out of the integration part. So integral A to B DL. So we know that what is integral DL? What is integral DL? What is integral DL? Integral DL is equal to L, sir. Integral DL is equal to L. Yes, integral DL is equal to L. So you will get it as length of the element. So if the rectangular ambient loop have a length L, from A to B, if the length is L, then you can simply write it as B into L, since we are integrating from A to B. The previous one we are integrating total, the closed loop integration we are considering. Here we are integrating from A to B only. Why? We have split up the total integration into 4 parts, and out of which one part is here, from A to B only is here. So it is equal to BL. Now we got the LHS equal to BL, right? So LHS equal to BL. So we can LHS, what we have got is, we have the equation closed integral B dot DL, both are vectors, is equal to mu 0 I enclosed, and what we have got is integral B dot DL is equal to LHS is equal to what we have got, BL. We have got it as integral BL. Now we can go for the RHS, mu 0 into I enclosed. I wish to call it as equation number 1. Then mu 0 I enclosed. Okay, mu 0 I enclosed is equal to, so I enclosed means the current that threading the length of the loop, right? So you know that this length doesn't carry any current, but you can see there are so many turns of the solenoid that threading through the length of the loop, right? So suppose suppose if n is the number of turns in unit length of the solenoid. If n is the number of turns in unit length, which means if you are considering 1 unit length, there will be n number of turns. If you are considering 2 unit length, there will be 2n number of turns. If you are considering L unit of length, there will be Ln number of turns, right? So total number of turns for the length L will be Ln, right? Total number of turns through the length L will be Ln. Why? Because number of turns in unit length is n. Then there will, for 2 unit length there will be 2n. For 10 unit length there will be 10n. For L unit length there will be Ln number of turns. Okay, so each turn there will be Ln number of turns, and each turn contributing for the magnetic field, right? Each turn is contributing for the magnetic field. Yes or no? So each turn contributing to the magnetic field means there will be, each turn carries a current I. Then total current that threading the loop which give contribution to the magnetic field will be taken as Lni. I will repeat once again. There are Ln number of turns, and each turn is contributing to the magnetic field, and each turn carries a current. So the total current that threading the loop which is contributing to the magnetic field is taken as mu 0, and current should be equal to Lni. Here Ln means total number of turns, and each turn carries a current I. So the total current that threading the loop will be Lni. Is that okay? Then put it as equation number 2, and equating 1 and 2, what will you get? You will get it as BL is equal to mu 0 Lni, and we can see L is common here, so L cancelled. Okay, so what we get remaining things? Okay, B is equal to mu 0, B is equal to mu 0 Ni, and this is the equation for magnitude of magnetic field due to a solenoid. This is the equation for magnitude of magnetic field due to a solenoid, and this is an important derivation in the class. As I said, be your own teacher and learn in such a way that you are going to teach your own, so that you can learn easy. Okay, so B is equal to mu 0 Ni, and one more thing, this magnitude mu 0 Ni will be available not in the end, only in the middle part. On the existence, apart from the end of the solenoid, you will get the magnitude as mu 0 Ni. But on the end or the B end, magnetic field at the end part of the solenoid will be as half of mu 0 Ni. So that is one more important equation. On the middle or the distance from end of the solenoid, there will be mu 0 Ni. The magnitude of magnetic field will be mu 0 Ni, but on the end the magnetic field will be the half of the mu 0 Ni, or B end of the solenoid is equal to mu 0 Ni. Okay, so when we plot a graph showing the intensity of magnetic field, this is magnetic field B. Okay, so this is the represent the length of the length of the solenoid, Okay, so if you are representing the length of the solenoid along the axis of the along the x-axis, and the y-axis we represent B. So we know that if this is the end point, okay, distance from the side, this is one end, okay, and this is another end of the solenoid. Then if the magnitude, this is B is equal to mu 0 Ni, this is the magnitude B0 Ni. So we know that on the end it will be half of that one. So the graph should be like this. On here it will be half, here it will be half, right? So the graph will be like this. Okay, so this point will be half of mu 0 So this is just a variation showing the magnetic field along the axis of a solenoid. On the mid part or the middle part of the solenoid, the magnetic field will be have maximum value which is equal to mu 0 and I, and on the end it will have not just a straight line, gradually decreasing, right? Then only the theory will be correct. Okay, it is gradually decreasing and it should be symmetric. It should be symmetric, like should be symmetric. So on the middle part or the distance from which is far little bit apart from the end, the magnitude will be maximum, and on the end it is gradually decreasing. Is that okay? So this is the graph showing variation of magnetic field along the axis of the solid. Okay, so we are going to wind up this session today, and we are moving to the last topic which I am going to discuss today. Okay, so which is electric Lorentz force and represented by the letter Fe, or F itself can be represented by electric Lorentz force. So what is electric Lorentz force? So this is what you have learned in the chapter 1 as well. Okay, so consider a charge Q is placed in an electric field, and the force experienced by the charge Q in the electric field Fe is equal to Fe, because E stands for electric field. Okay, so force experienced by the charge in the electric field placed in the electric field Fe is equal to QE, that you have learned in chapter 1, Coulomb force, nothing else, it is the Coulomb force. Okay, so force experienced by the charge placed in an electric field is known as electric Lorentz force. There is another name for that force, Coulomb force. It is electric Lorentz force, and we didn't mention the name electric Lorentz force in the first chapter. Instead of that, we are mentioning it here. Okay, force experienced by a charge Q placed in an electric field D, it is given by Fe is equal to Q into E. I am just recollecting it and nothing else. Okay, so this is the important topic in this chapter, belongs to this chapter. Force on a moving charge in a magnetic field, or else we can call it as magnetic Lorentz force, and represented by the letter Fm. M belongs to magnetism. Okay, so consider a magnetic field B, Okay, so it is directed from left to right. Okay, so here it is a moving charge, right? So consider a charge Q, which is moving in the magnetic field with the velocity v. So this is a moving charge, it is moving with a velocity v, and the direction of b and direction of v both are vectors, right? So this is also vector. So these vectors making an angle. So the direction of velocity of the charge q making an angle theta with the magnetic field. Okay, so Lorentz force is given by, and there are some more proportionalities here. Okay, so this Lorentz force is directly proportional to magnetic field. And second one, this is first one. Okay, second one, this Lorentz force is proportional to the magnitude of charge Q. And third and last one, this Lorentz force, magnetic Lorentz force, is proportional to V, the sign component of the velocity. Okay, so magnetic Lorentz force is proportional to B, and magnetic Lorentz force is proportional to the charge, and magnetic Lorentz force is proportional to V sin theta. And I wish to write it together like Fm is proportional to Q P P sin theta. That okay? Fm is proportional to QVB sin theta. You should write in this order as well, then only it will be correct. Okay, so the purpose we are writing in this particular order, you will understand it later. Okay, so Fm is proportional to Q and V and B and sin theta, right? So together QVB sin theta, and it is easy to read, right? QVB sin theta. F is equal to Fm is equal to here the constant of constant of proportionality is 1, so that I can write F is equal to QVB sin theta. So this is the expression for yes, This is the expression for magnetic Lorentz force. Okay, Fm is equal to, or F is equal to 2Eb sin theta. Okay, so here you know that V is a vector, magnetic field is a vector, so that this equation can be also written like F is equal to Q into velocity is a vector, magnetic field is a vector, so Q into V cross B, because V cross B is Vb sin theta. That's why we are interested to write in this order. V cross B is Vb sin theta. So Fm is equal to Q into V cross B. Okay, so this is the expression for magnetic Lorentz force. Okay, so now what we have is the special case for that one. Okay, so we have the equation Fm is equal to QVB sin theta. Okay, so first special case, if velocity is equal to 0, what if velocity is equal to, will not be a force. If the charge is not moving in a magnetic field, charge is at rest, there will not be magnetic Lorentz force, that charge. There will not, if the charge is not moving in the magnetic field, if it is stationary, there will not be a magnetic Lorentz force. But in the case of electric field, if a charge is placed at rest in an electric field, it experiences a force given by F equal to QE. But in the case of magnetic Lorentz force, if the charge is at rest, there will not be any force. Okay, so the second case is regarding, we have sin theta here. Okay, theta equal to 0 means, what is theta equal to 0 means? Theta equal to 0 means sin 0 is equal to 0. So F equal to M is equal to sin 0 is 0. Okay, one more thing, if theta equal to 90 degree means, 90 degree implies Fm is equal to, what is the value of sin 90? Sin 90 is equal to 1, sir. So it will be, Fm will be equal to QVB, which is the maximum force M maximum, right? So what is the implication of this one? What is the implication? What is theta? Theta means angle between V and B. Theta is 0 means V and B in the same direction or in the opposite direction, moving in the opposite direction. So theta will be 180. Okay, so if the charge is moving along with the magnetic field, means theta is 0. So force will be 0. So if the charge is moving along with the magnetic field, force will be 0. And if the charge is moving perpendicular to the magnetic field, theta is 90 degree. If the charge is moving perpendicular, theta is 90 degree. So that what is the force here? Force here is maximum. So if a charge is moving perpendicular to the magnetic field, force will be maximum. If the charge is moving in a same direction or in the opposite direction, theta equal to 0 or theta equal to 180, so that force will be 0. So a charge moving parallel or in the same direction or in the opposite direction to the magnetic field doesn't experience a force. Is that clear? Then give me thumbs up for fire emoji. Let me see. Trust me, Rahul sir. Okay, Rahul sir. Okay, nice. Who is that? Trust me. Okay, thank you then. So then we have Lorentz force. What is Lorentz force here? What we have discussed is electric Lorentz force and then magnetic Lorentz force. Magnetic Lorentz force, electric Lorentz force. Then what is Lorentz force? It is nothing but when the charge is moving in an area in which there will be combined field of electric and magnetic field. If the charge is moving in an area in which there are electric and magnetic fields are present, then the charge will experience a force called Lorentz force. So I will explain it once again. We have electric Lorentz force and magnetic Lorentz force. But Lorentz force means when a charge is moving in an area in which electric and magnetic fields are present, the charge will experience a force called Lorentz force. Okay, that's the definition for Lorentz force. Okay, so it is equal to Lorentz force given by F is equal to sum of electric Lorentz force as well as magnetic Lorentz. What is the expression for electric Lorentz force? Electric Lorentz force is F is equal to QE plus what is the expression for magnetic Lorentz force? It is equal to Q into V cross B sir or QEB sin theta sir. Yes, we can simply write it as Q into V cross B. Okay, so Q is common sir, common. So Q can be taken outside of the bracket. So Q into E plus. Okay, E plus, what is remaining there? E plus V cross B. So this is the expression for F is equal to Q into E plus V cross B. This equation will be helpful for you to solve some numericals or solve some numerical or some problems in entrance exam. For board exam, I think I didn't see any question regarding that in the board exam in the previous years, but in the NEET or JEE exam, there will be questions using this equation. Okay, so one more thing, a charged particle moving perpendicular to the magnetic field will follows a circular path. Okay, a charged particle which is moving perpendicular, if the magnetic field is in this direction, this is magnetic field, and if a charged particle is moving perpendicular to it, due to the Lorentz force, the charge will possess circular path. It will possess circular path. Okay, so that's an important point. A charged particle moving perpendicular to the magnetic field will follow a circular path. Okay, then what happened? What happened if the magnetic field is like this and electric charge is moving with an inclination, as I saw it in the previous slide? If the velocity makes an angle theta with this is velocity and this is magnetic field, if it make an angle theta with the direction of magnetic field, what happened? Does it follow a circular path? Let's see, and after that we can wind up the session. Okay, so here we have, consider an axis. This is the axis and this is the velocity vector. Sorry, I mark it with another color. Okay, yes. So this is the velocity vector v and making angle theta with the x-axis. Okay, so to understand it clear, I wish to split its rectangular component is equal to, so this is theta, right? So this velocity component which is adjacent to theta, adjacent side is sine, cos or sine, cos theta, right? So it is v cos theta and it will be v sin theta. The rectangular components will be v sin theta and v cos theta respectively. Okay, so if this is the direction of magnetic field, so v cos theta and b are in the same direction. So angle between v cos theta, velocity component cos theta, and magnetic field is 0. So if charge moving in the same direction as that of magnetic field doesn't experience a force. So due to this v cos theta component, there will not be a force. But what about v sin theta? It is perpendicular to the magnetic field, angle is 90 degree, right? So due to that 90 degree angle, theta is 90 degree, it will possess circular path. A charged particle moving perpendicular to the direction of magnetic field will have a circular path. So due to v sin theta, there will be circular motion. Okay, but v cos theta doesn't have any force. So it will possess circular motion. The charged particle possess circular motion. Along with that, due to this cos theta component, it will move in the x direction. So along with the circular motion, it is moving in the x direction. I will show this once again. Along with the circular motion, it is moving in the x direction, so that it will possess helical path. It will possess helical path. Circular motion along with the y directional movement. So it will be a circular path. Okay, so a charged particle moving with an inclination will possess helical path. A charged particle moving perpendicular to the magnetic field will have a circular path. Okay, so that's all of today. I hope all the topics are clear today, and if you have any doubts, just comment in the comment box. I can explain it once more, or else we can wind up the session. Okay, so dears, on 9th September, this coming Saturday, we have our Satyan sir, the academic head of Goscore, who is coming up with his second part of the chapter 5, continuity and differentiability of chapter 5 of grade 12 maths. Okay, so stay tuned, and we can meet up in the coming class. Okay, so by then, happy learning. So